Welcome to Module 204G on Single Motor Control Pilot Devices and Symbols. We have a lot of different objectives to cover within this module, so we will be dividing these into two separate videos. Part 1 is going to be based on objectives 1, 2, 3, and 4. Let's start with objective 1, where we look at the three basic sections of a stop-start control circuit. By now you should be able to recognize a basic stop-start 3-wire control circuit where we have a normally closed button for our stop, a normally open button for our start, a normally open contact for our holding contact, and then we have our relay coil and our overload device. One thing you may not be aware of is that each part of this circuit has a very specific function, and we need to be aware of what that function is because we can put other devices into these sections in order to accomplish different tasks. The first section we're going to look at is our stop circuit. Inside our stop circuit are going to be all the different types of devices that are responsible for stopping the circuit from operating and will de-energize the coil. Within the circuit, all these devices will be arranged in series. Next to my stop circuit, I have my start circuit. So these are going to be all the different devices that are responsible for energizing that coil. And these are all going to be placed in here in parallel to each other. So each one can independently start the circuit. The third circuit is my holding circuit, and within this area I'm going to put all the different devices that are going to be responsible for making sure the coil stays energized regardless of the state of the start circuit devices. Each one of these different circuits are responsible for a different function within my overall circuit, such as my starting circuit is responsible for initially energizing the motor coil. Once the coil is energized, the holding contacts will shut and therefore providing a secondary path to my motor coil. So the job of my holding circuit is to provide an alternate path to my start circuit. Once I release my start circuit, my holding circuit stays closed, which will make sure I maintain an energy source for my motor coil. And the only way I can interrupt that energy source is by activating my stop circuit. If I activate any of my stop devices, it should interrupt the total flow of electricity through the entire circuit. So therefore I will de-energize the coil, which will open up the holding circuit. As we go through this module, we're going to be looking at adding different components into each one of these three circuits, and we're going to evaluate what the reaction of the circuit is going to be as we start to manipulate things. Make sure you understand the purpose of each one of these different start, stop, and holding circuits and what their overall function is towards the entire circuit. In Objective 2, we're going to look at the operation of a control circuit when we're using interlocks. And we're going to start to place those interlocks into my start, my stop, and my holding circuits to see what the overall effect is going to be. When we look at this schematic, we should be able to identify two separate circuits. First, we have our motor control circuit, which is our typical 3-wire stop-start station. And then we also have a control relay that's being operated by a thermal switch. The intention here is to have an interlock in between those two circuits. In order to understand this, we need to review what an interlock is. An interlock is an automatic or manual control that is wired into another control circuit. And the function is to interlock the control circuit with another condition, such as pressure, temperature, or the operation of another device or another load. And where we put the interlock controls depends on the design requirements and the needs that we have. For example, if we're to put the normally open contacts from the control relay into the stop section of our motor control circuit, we're going to look at how that's going to affect the circuit overall. You'll notice that the thermal switch that controls the control relay is a normally closed switch, which means that when everything is cool, then the control relay is going to have power and the normally open control relay contacts are going to be closed. When the heat gets too high, that switch is going to open, which will de-energize the control relay, which will open up the control relay contacts. When we first energize this system, we can see that the normally closed thermal switch has energized CR. That means CR contacts are closed. This gives us a completed path from line 1 all the way up to my start button and to my normally open holding contacts. When I hit the start button, M1 is going to energize, M1 holding contacts are going to close, and the motor contact is going to work fine. But what happens when we have a temperature rise? If this circuit is running and my M1 contactor is operating, and I have a thermal rise that is enough to open up my thermal switch and de-energize my control relay, the normally open contacts in the stop section of the circuit are going to open, which is going to interrupt the current flow for the rest of my M1 motor contactor. When the contacts are used in this way, this is a means to automatically de-energize my motor contactor if the temperature is too high. This will also prevent me from starting my motor contactor if the temperature is too high to begin with. So when my circuit is de-energized and the temperature is too high, the control relay will not energize, the CR contacts will not be closed, and there's no way for me to get power over to my M1. So having my control relay interlocking contact in the stop circuit does two things. It prevents me from starting the motor if the temperature is too high, and if the motor has already started and then the temperature rises, it will automatically stop the circuit. If we move the CR contacts from the stop circuit into the start circuit, things will change a little bit. Now, when CR is energized, my control relay contacts are closed, my 3-wire circuit will act like a 3-wire circuit always does. If I press my start button, it will energize M1, which will close M1 contacts, and it will continue to run as it is. If the temperature was too high before the motor was started, the CR contacts being in the start circuit in series with my start button is going to prevent me from starting that motor at all. So with M1 being de-energized, the CR contacts are open. If I hit my start button, I'm not going to get any power through that section of my start circuit, so therefore M1 will never energize. However, if CR is energized and my CR contacts are closed, I can start M1 normally. But what happens if my motor contactor is running and then the temperature gets too high? Before, when the interlock contacts from the stop circuit, we saw that it de-energized that entire circuit. This time, I have continuity through my M1 holding contacts, and since my CR are in my start circuit, they're not going to de-energize the holding contacts at all. So if my motor is already running and the switch controlling CR opens, then my motor will continue to run because my holding contact is bypassing the CR contact. Lastly, we're going to look at what happens when we put our CR contacts into our holding circuit. Now, with my thermal switch being closed, everything will still operate as a normal 3-wire control, where if I press the start button, M1 will energize, which will close contact M1, and since my thermal switch is closed, CR is energized and my CR contacts are also closed. This gives me continuity through my holding path. If my M1 is not started yet and my thermal switch is open, therefore CR is not energized and my CR contacts are open, if I hit my start button, it will energize M1 and it will close the M1 contacts. However, as soon as I let go of the start button, since the start button is a momentary contact start button, we're going to de-energize M1 because I don't have an energy path through CR. Remember, if the thermal switch is open, then CR will also be open. Let's look at what happens if M1 was already energized before the thermal switch opened. If CR is closed because the temperature is low, and I press the start button, which energizes M1, which closes the M1 contacts, both the CR contact and the M1 contact that are both in my holding circuit will be closed. This gives me an alternate path. I can let go of the start button, M1 will stay energized. If the temperature starts to rise and the thermal switch controlling the CR coil opens, then my CR contacts will open as well, which will disconnect the holding path and my motor contactor will start. The interesting thing is that if the temperature is still high and CR contacts are open, I can still run that motor just by pressing down the start button. So instead of it operating like a normal start button, it now becomes a jog button because I can just simply move the motor a little bit just by pressing the start button. And the motor will not be energized for any longer than I have that start button pressed down. You can see that when it comes to interlocking, where we place that interlocking contact can make a significant change within our circuits. We have to decide what our circuit wants to act like. Do we want to be able to stop it from running and stop it from starting? In which case we would use our stop circuit. Do we want to stop it from starting but not stop it from running if it has already started? Then we're going to put it into our start circuit. Or do we want to stop it from running but not stop it from jogging, in which case we're going to put it into our holding circuit. Deciding how to design the circuits depends a lot on what kind of components we have to deal with and what kind of function that we want to use. Now that we're familiar with the three different sections of a typical stop-start circuit, we're also going to look at what that circuit is going to look like when we have more than one stop-start station. A simple machine like an exhaust fan would only ever require one stop-start circuit. However, when you look at more complex systems, such as conveyor belts, we need to have that level of control at multiple different locations. And we need to know how to arrange all of our devices so that it's going to work appropriately. Having multiple stop-start locations inside my schematic diagram is fairly straightforward. Every device that is responsible for stopping the circuit needs to be in the stop section of the circuit itself, and all those stop devices are going to be placed in series. The reason for this is I want to be able to press any one of those stop buttons to interrupt the flow of current. Therefore, if they are all in series, they will all have master control over the entire circuit and they will all be able to shut the circuit down. When it comes to my start devices, I want to have all my start devices in the start section of my circuit, and I want them to be all in parallel. The reason I want them to be all in parallel is I want to be able to press any one of those start buttons to be able to start the motor. This makes them all master controls as well. As long as you remember that all your stop buttons are going to be in series and all your start buttons are going to be in parallel, doing a schematic diagram with even 10 stop-start stations is a fairly simple process. When we transition from a schematic diagram to a wiring diagram with multiple stop-start devices, it can get a little confusing, but we're going to apply the exact same rules that we use with our schematics. All of our start buttons must be wired in series. Therefore, we're going to plan to come from our supply inside our contactor to my very first and my closest stop button. From there, we want to have a wire going to each consecutive stop button after that. After we reach the final stop button, that's where we're going to transition from my stop circuit into my start and holding circuit. With my start circuit, all my start buttons are to be wired in parallel, so I want to make sure that from each terminal on each one of my start buttons, I am going in parallel to all the other start buttons, working my way from the furthest start button all the way back towards my contactor. The last thing I want to do is to make sure that my start buttons and my holding circuit are also in parallel. So when I come into the contactor, I want to make sure that the wires that are coming from my start buttons go parallel to my holding contact. Hopefully you noticed that the way I structured this was to go to the closest stop button first, work through all my different stop buttons as I get further and further away from my motor contactor, and then go to my furthest start button and work my way back towards the contactor. There is another way we can do it, but it's not quite as efficient. If I were to go to my very last stop button first, I would have to go all the way to the very last location. Then I'd have to start with my series connection through all my stop buttons, going back toward the contactor again. After that, I would have to parallel my start button, starting with the closest start button to my contactor and working away from it, as well as working back into my contactor to go parallel to my holding contacts. Now, as you can see, I've gone from having 3 wires between each device to now having 4 wires on each device. This causes a couple of problems. First, it's going to take more time and energy for you to install it. Secondly, it's going to take more money to buy that extra wire. And thirdly, depending on the voltage of the system and the distance of the wire, we could have problem with voltage drop, because as that wire has to go that further distance, I've also increased the resistance of that wire as well. In objective number 4, we're going to look at a very specific type of device that is not a control device at all, but it is an indicating device. In fact, it is an indicating light. We're going to look at a few different places that we can put the indicating light, and then we're going to look at what that indicating light is going to be telling us. In a simple motor control, we can have a number of different places where we can place indicating lights. Here are 3 most common places that we can put our indicating lights. Our first indicating light is our power on indicating light, and it's connected directly between line 1 and line 2. With this light, I don't have to pull out my meter to determine whether or not I have power to my system because it's already indicating that I have or have not. If I blow my fuse, for example, this light will not be on and I know that I have a problem right away. Our second light is a run light, and it should indicate whether or not the motor that we are controlling is in operation or not. What it's really telling me is whether or not my M1 contactor has closed my M1 holding contacts. In relationship, this should also close all my power contacts, so my motor should be running, but it gives us a clear indication of whether or not my contactors are working. It's always placed in parallel to the contactor, so as soon as my contactor gets the energy, my light also gets energy, and I know that they're both working together. The last indicating light I have on this drawing is for my trip setting. With my overload on my IEC contactor, I will have a normally closed contact and I'll have a normally open contact. My normally closed contact I'm going to wire in series with my motor controller. However, I can use the normally open contact to indicate whether or not I have a trip setting. Remember, when the overloads trip, it will change the state of that contact. So when I do have a trip situation, it will close this set of contacts and it will indicate that something has happened to my motor circuit. Depending on the type of circuit that you can have as many indicating lights in there as you want, all depending on what you want to have indicated for you. This circuit is for fan motor control, and it has my power light, it has my on light, it has my off light, it has a trip light, and it has an airflow light. So now I can see what the state of the motor is at any point in time, whether or not I have power to the circuit, whether it is operating or if it is not operating at the time, whether it is in trip status, or whether or not I have any airflow. I can always add more pilot lights to my circuit depending on the type of initiating devices I also have related to that circuit as well. We've now reached the end of 204G Part 1. Make sure you are reviewing the first 4 objectives in this module, and then you can continue on to 204G Part 2.